In this experiment, you will validate one of the basic assumptions of quantum mechanics, wave-particle duality. You will also observe the diffraction patterns of light and electrons and use these to determine the spacings between the scattering features in different samples. Different wavelengths of light diffract from a grating at different angles. The diffraction equation relates the diffraction angle, wavelength, and spacing between grating features. d sine theta equals n lambda. The groove spacing can be determined from knowledge of the angle of diffraction at different wavelengths and the diffraction orders. This experiment consists of two parts. In the first, you'll use 3 different wavelengths of light in order to determine the feature size of grooves on a compact disc CD. Be very careful when using the laser pointers. Although these are low-powered beams, they can still cause a lot of damage if you look directly into the beam. You can perform all of the measurements in this experiment using rulers and yardsticks. The first measurement that you should record is the distance from the CD to the wall. For each wavelength of light, you'll also need to measure the spacing and separation between the different diffraction spots seen here. You can see the central, the first, and the second order spots. Using this and the distance to the grating, you can calculate the angle. For the second portion of this experiment, you're going to be using a specialized apparatus for electron diffraction. In this apparatus, an electron beam is accelerated from a cathode towards a graphite lattice where it diffracts. The diffracted beam is visualized by ring patterns on a phosphor screen. As one final note, be sure you have all of your measurements done in triplicate before leaving lab. You'll need this in order to perform uncertainty calculations.